Hello and welcome. As promised, another first order differential equation for further mathematicians. Not as hard as the one I presented the other day, and it's 4.5 star. and the reason not as hard is because the technique is equally involved. However, this particular differential equation, for those who have seen substitution into further maths, if you prefer, they can do that though longer by some kind of substitution, a homogeneous substitution. So if we have enough time, I'm going to do it two ways. So first of all, the technique that I'm going to use, that I will try to give you some practice, is when we're having a standard first order differential equation and the one with integrating factors, and the x's and y can be swapped around to produce what we want. So I'll write this particular differential equation. 2y minus x. I'm not doing anything, I'm just writing it again. Is equal to y. X and y are positive, and is giving us a boundary condition if the curve goes to the point 2, 1, to show that the equation of the curve is x is equal to 1 over y plus y. So what do we do first? We want to swap the x and the y, so probably the best thing to do is to divide first of all the bracket. dy by dx is y over 2y minus x. I do apologize, I'm not very well today, so I keep coughing an awful lot. And this is homogeneous, which if I have time, as I said, I'll come back to it. But for the time being, we don't know anything about that. So we're going to swap dx by dy, flipping this bit here, is equal to 2y minus x divided by y. What should we do next? Maybe times the y across, make it a little bit neater. Dx by dy is 2y minus x. And then possibly take that x to the left. So far so good. And if we notice that this bit here is in fact exact, is in fact the differential with respect to y of xy. Let's check it. Differentiate the x with respect to y, gives us dx by dy. Second bit unchanged. And now leave the x bit alone. Okay, here it is. Differentiate the y with respect to y is 1. So that's all good. Just if you can't quite see that, if we take it, let's say, to this line here. Actually, we don't have it on this line, but let's take this quantity and rewrite it as dx by dy, divide just the y through, so brings, sorry, I beg your pardon, it's not quite what I wanted. I wanted this one, plus x divided by y is equal to 2. Then look for an integrating factor. Why is that? It's because the standard differential equation, first order, is dy by dx, not dx by dy, plus yf of x is equal to some function of x. So if we look at swapping x and y's here, we have dx by dy plus x f of y is some g of y. This is basically your 2. This is your 1 over y. That, of course, is your x. And this is, of course, upside down. So your integrating factor here should be e to the 1 over y dy, which is e to the log of y, which is y. And therefore, this particular thing, if we times it, the left-hand side will become exact. So it's going to be d by dy of xy, and the left hand side needs to be times by 2. So of course we're getting exactly the same thing. Okay, so it will still work, but this is almost enrichment here, and we should be able to spot all of this. So from this point onwards, the differential equation is just very simple. Integrate both sides with respect to y. Xy is equal to y squared plus a constant. Probably apply the condition to 1 at this stage. So that's 2 is equal to 1 plus a constant. The constant is, of course, 1. So we're getting xy is equal to y squared plus 1. And if we divide both sides of this equation by y, remember y is positive, so we can do that, it's as required. What does this curve look like? Well, the question doesn't actually ask. This is the graph of y is 1 over x plus x. We should be able to sketch it very quickly. Close, first of all, this is an odd function, so it's symmetrical, has rotational symmetry about the origin, 180. Close to the to x is equal to 0, it looks like the curve 1 over x. And as you move away, big X, it looks like the line y is equal to x. So it looks something like this. That's not the one that we got in here, but the one that we got onto there. So this swapping x and y is just a mere reflection about the line y is equal to x. So it will look something like this. So the one in orange that I'm putting in there is, of course, x is equal to y plus 1 over y, if the question, of course, asked for something like this. Okay, so the question is done. As you can see, once we've done this initial manipulation, swapping with the intention to swap x and y, everything works really, really well. This is not actually even hard. But I'm going to do an alternative method, because this, even if you don't spot this particular manipulation, can be done by a substitution, which although is more standard. I mean, if I was to look at this particular differential equation myself, I certainly wouldn't have spotted the swapping the x and the y's. How come I spotted it here? Is because I made the question quite clearly, so I knew what I need to do. So first of all, let's divide this bracket. And I did say when I did divide it, that this is homogeneous, which means the right-hand side, on the fraction of the right-hand side, everything is of a function of x over y or y over x if I divide it through, or you can, or the brain sees it, all powers of of 1 here. So the substitution that works for something like this is very, very simple. It's a standard substitution. Is y as a function of x is x v of x. So oops, dy by dx, I'm gonna leave the arguments, is of course 1 v of x plus, leave the x alone, x dv by dx. I'm not gonna change the boundary conditions, I'm gonna move it back at the end. So we have v plus x dv dx, that's this bit here, is equal to y is xv over 2xv minus x. And the reason this works is because, of course, in this particular expression, all the x's will disappear. So we have v plus x dv by dx is equal to v minus 1. Take the v to the other side, so this will separate basically. dv by dx is v over 2v minus 1, x dv by dx. This is longer, as I told you, but and I don't know how difficult the integration will be at the end of all of this, but this is very, very standard. It's, I think, in most boards, substitutions from differential equations appears in kind of like extra further maths. I call it further maths. I don't know what modules, different boards use different names. So we got my v, that's this v here, put to the same denominator, 2v minus 1 minus 2v squared plus v. I got one more line to write this. dv by dx is equal to 2v minus 2v squared over 2v minus 1, which is not very nice, but at least the variables separate. And because we need to go back into v, v is in fact y over x when we are ready. So for the time being, we're going to separate the variables. 2v minus 1 over 2v minus 2v squared dv. So this is now from this line here. is equal to, this will go as 1 over x on the left, sorry, on the right, I beg your pardon, dx. So we're going to have some kind of logs there. And I know there's no logs in the answer, so that's some kind of log very, very easily. How are we going to do that? Probably pull out a factor of -1/2 on the outside. So it's going to give us 2v minus 1. The signs will swap and the 2 will go. So that will be a v squared minus 1. No, minus 1 minus v, I beg your pardon. So it's of the type bottom differences to top. So 2v minus 1 dv is equal to 1 over x dx. I'm going to do two things at once. So this now integrates very, very easily to log of v squared minus v. You can use mods if you want. And this is going to go onto the other side as a -2. So if it goes as a -2, it's going to be -2 log x. And because we got more logs, let's put plus the log of c or log of a or whatever you want to call it. And let's get rid of the logs. Log v squared minus v is equal to, I'm going to move that as this -2 as 1 over x squared and then add the log. So it's going to be the log of a over x squared. And I think we're almost there because now we have v squared minus v. We can get rid of the logs. We still have boundary conditions to put in. So let's make some space, first of all. And then we'll put, first of all, we need to put x's and y's back in. And then we'll put the boundary conditions. And we should get exactly the same answer we got before. So v squared, so this now gives us y squared over x squared, that's this bit here, minus the v, which is y over x, is equal to a over x squared. Probably put the boundary condition now. So we have 2, 1. So this will give us 1/4. This is now -1/2 is equal to a over x is 4. So multiply the equation by 4. 1 minus 2 is equal to a. And we have a in this particular case is -1. So we have, that's the boundary condition here. Multiply the equation first of all. Actually, let's put the -1 rather, in first of all, so we don't make any mistake. Y squared over x squared minus y over x is equal to -1 over x squared. Multiply the expression now by x squared will give us y squared minus yx is equal to -1. Divide the equation by y will give us y minus x is equal to -1 over y. And if we rearrange it, we'll get x on this side is y plus 1 over y as before. Remember, we can divide by y there because y is a positive number, cannot be 0. And we got, of course, exactly the same answer as before. I hope you followed this particular differential equation. This is the end of this lecture. I'll be seeing you very, very soon. And on this note, I am signing out.